Hi, in this video I am explaining full chapter of pharmaceutical complex, or you can say complexation chapter. It has been explained fully, hence the video is a bit lengthy. Okay, please listen to this carefully and you will get full knowledge of complexation chapter. Hi, today we are going to learn about pharmaceutical complex, or simply we can call it as a complex. First we try to see what do you mean by complex. What the name complex suggests about. So the name complex says something which is not simple or which is not understood simply. So in terms of chemical complex, if any bonds, see generally we have many bonds. Let's say if you are taking any atom, if I take carbon, we have some bonds to the carbon. It may be double bond, it may be single bond. Okay. So these bonds are explained by classical theory of valencies. So we have theories which will explain how the bond is going to form. For those theories, the name is classical theory of valencies. Now, in complex, there will be, let's say there is a complex formation, okay, between cobalt and something else like this. Okay. In complex, we have bonds, one or two bonds. All bonds are will be explained by the classical theory of valencies in the complex, but in complex, some of the bonds were not explained by our classical theory of valencies cannot explain the formation of those types of bonds. We call them as anomalous. The bonds are anomalous. You can't explain those bonds. See, so in a complex we have uh, many bonds. In that, one of the bond is not explained by your classical theory of valencies. Hence, we call that compound as complex. So this compound is been called as complex. So that was the definition for the complex. So now we will move on. Which type of bonds are going to form between the atoms in a molecule? Yeah, you can clearly see here. Yeah, you can clearly see here we have these types of bonds which are going to form between the atoms in the complex or in a molecule. One is your covalent or coordinate bonds. Then we have van der Waals force of dispersion. Then we have ionic dipole and dipole and dipole induced dipole, and then we have hydrogen bond. So these are the bonds which are formed in the complexes. Now the complex may possess the properties which are different from the components. Okay, so overall when the complex is formed, this complex has a different property compared to its components because it is a complex. Altogether the molecule is different, hence it has the different properties compared to its component. Properties such as solubility, light absorption, conductance, partition behavior, chemical reactivity, okay, etc. These properties are vary. What I mean to say is, if you take the components of complex, so that complex component, one of the component is more soluble. After forming the complex, the whole complex is not soluble. That's what I mean to say. Like this, you can have different types of change in the properties like solubility, light absorption, conductance, partition behavior, and chemical reactivity. Then complexation behavior is observed in number of situations including handling of dosage forms. So we observe this complexation in the handling of dosage form. Hence it is utmost important for us to study about or to know about what is the complex and what are the complications we have. So we will see some of the examples for that. Now we will see some of the examples where we have complexation situation in a dosage form. So complex has drugs. There are a few examples of drug complex. Few examples of drug complex are mentioned here. So one example is cisplatin. We call it as a DDP, cis dichlorodiamine platinum 2. Trade name is platinol. Okay. No, this forms a complex. This itself is forming a complex. Check here. So here the bonds, two bonds can be explained by classical theory of valency. The chlorine bond can be said as a covalent bond. It is explained by classical theory of valency, which is found by the sharing of atoms. But these two bonds cannot be explained by classical theory of valency. We have different bonds here. I will show in different color. So these two bonds are explained by classical theory of valency, and these two bonds cannot be explained by classical theory of valency. Hence, we call this particular molecule as a complex. Now, this is a coordination compound. We'll check about this compound. This is a coordination compound that has broad application in human cancer therapy. So we use this in human cancer therapy. Okay, it has a divalent platinum. See here, platinum. Platinum is a divalent bound to two potentially leaving groups, that is chlorides. So it's bound to two potential leaving group, that is your chlorides. It's a divalent, and also it bounds to two amino groups which are bound irreversibly and in form coordinate covalent bond. Okay, so here we have two amino groups which are held by coordinate covalent bonds. Okay, structure is like this. So this was the structure of cisplatin. Why call it as cisplatin? Because two chloride groups, I will just show you here. Both the chloride groups are the same side. If the one of the chloride is here, and if one of the amine group is here, then we call it as a transplatin. Okay, we call it as cisplatin because we have two chloride groups at the same side. Next, we have povidone iodine. So your polyvinyl pyrrolidone (PVP). Polyvinyl pyrrolidone is a water soluble polymer. So PVP we have, it is a water soluble polymer. When you add iodine to this polymer, okay, it will form a complex which is also water soluble with the iodine. The structure of this povidone iodine is given below. We will try to see the structure in the later parts. Okay. Yeah, see, this is the structure of povidone iodine. So we have iodine here. See, this is the iodine which is been entrapped in the polymer PVP, polyvinyl pyrrolidone. Okay. So we have pyran groups here, hence we got pyrrolidone. Okay, polyvinyl pyrrolidone in which the iodine is entrapped. Now because this iodine is soluble and the complex which is formed is also soluble, not iodine is soluble, sorry, the PVP is soluble and the complex which is formed is also soluble. Hence, we get to remove the drug from the site of application. Means what? If you apply this ointment, it is available in the form of ointment, solution, etc. So if you apply this to the site, okay, where it is required, let's say if you have wound on the hand and you applied this, after you put water on the site of application, everything will be washed out because the complex which is formed, povidone iodine complex, is soluble. As such, your iodine is not soluble, but when you add povidone iodine, PVP, it forms a complex and the complex is soluble, hence we can wash it very easily. Then we will see the few applications of complex. So physical state, you can change the physical state of a molecule, you can change the physical state. For example, we have nitroglycerin which is available in the form of liquid. This nitroglycerin is transformed into solid by the complexation with cyclodextrin. Remember, GPAT question. Okay, nitroglycerin is transformed into solid by the complexation with cyclodextrin. So this type of complex we call it as inclusion complex. Inclusion complex, because your nitroglycerin will be included into the cyclodextrin structure, we call it as a inclusion complex. So what we are doing here, we are taking nitroglycerin which is in liquid form, we are complexing with the cyclodextrin, the resultant complex is solid, and that solid contains 15.6% of nitroglycerin, and it is explosion proof also. See, nitroglycerin as such is explosive. If you expose it to the sunlight also, it will get exposed. Sorry, uh, explosion. It will cause explosion. Now, to avoid this, if you convert that into the solid, you can avoid the explosion of nitroglycerin, and you can stabilize it by forming a complex with the cyclodextrin. Next, we have volatility. If you want to reduce the volatility of any substance to stabilize it, okay, then what can we do is you can convert that into a complex. The best example for is polyvinyl pyrrolidone complex. So, PVP, polyvinyl pyrrolidone complex, your iodine is highly volatile. If you keep as such, the iodine will, once you open the box, the iodine will start volatilizing. Okay, to avoid this situation, we try to complex this iodine with the polyvinyl pyrrolidone, and we will get a complex which will hold your iodine in firm way, so that iodine can't escape through volatility. So, the volatility of iodine can be reduced. Next is solid state stability. So, solid state stability of drugs can be enhanced by complexation. What do you mean by this? Example is beta cyclodextrin with vitamin A and D. So, vitamin A and D are not stable as such. They tend to get oxidized, okay, very easily. To avoid this oxidation, you can complex the inclusion complex with the beta cyclodextrin. Remember this, beta cyclodextrin for the solid state uh, stability in terms of vitamin A and D. Those vitamin A and D, these vitamins are highly unstable, they undergo oxidation. To avoid this or to increase the stability, we will form a complex with the beta cyclodextrin. Next, chemical stability. You can alter the chemical reactivity either by inhibiting or enhancing the catalytic effect. Okay, how can we alter this? For example, see there, the hydrolysis of benzocaine. Benzocaine, it is a anesthetic, okay, local anesthetic. This benzocaine is highly oxidative. It undergo hydrolysis also very easily. Okay, it undergo hydrolysis very easily. Hence, what we'll do, we'll form a complex with the caffeine. We call it as a organic molecular complex. Okay, we form a complex with the caffeine. Once the caffeine form the complex with the benzocaine, this complex is highly stable and it tends to undergo hydrolysis very less compared to the plain benzocaine. So, we can increase the stability, chemical stability also. Next one is solubility. You can alter the solubility. Okay. See, at low concentrations, your caffeine enhances the solubility of para amino benzoic acid. If the concentration of caffeine increases, again it will decrease the solubility by forming higher complex, which we are going to study in the later part of this chapter. At low concentration, caffeine will increase the solubility of para amino benzoic acid. Then we have dissolution. You can alter the dissolution also. So, your dissolution rate of phenobarbital is a drug. This drug is having dissolution problem, it has solubility problems. So, your dissolution or solubility characteristics can be enhanced by complexing with beta cyclodextrin. Again, it is a inclusion complex. So, by forming an inclusion complex with the beta cyclodextrin, the dissolution characteristics of your phenobarbital is increased. Remember this example for the particular thing. So, dissolution characteristics is enhanced by forming a complex with phenobarbital. Phenobarbital dissolution characteristics is enhanced by forming complex with the cyclodextrin. Next, we have partition coefficient. Here, for example, the partition coefficient of your drug can be changed. You can change the solubility, hence the partition coefficient can also be changed. For example, permanganate ions can be transferred into benzene phase. So, if you take benzene water system, we have benzene here and we have water here. Initially, the permanganate ions are soluble in water, they are present here. When you form a complex with crown ether, when you add ether to the permanganate ions, this ether forms a complex with the permanganate ion and it will slowly shift your permanganate ion to the benzene. Previously they are present in water partition, slowly they are shifted to the benzene. What is going to happen here is, due to formation of complex, there is a change in a property which we studied in the earlier. Here the property is your partition coefficient through ion pair mechanism. Next, absorption and bioavailability. Okay. You can increase or decrease the absorption of drug by forming a complex. Okay, the best example for this is tetracycline, which form a complex with divalent cations such as calcium. That is calcium, magnesium, aluminum. This tetracycline will form a complex. So if you are given with a tetracycline drug, don't take milk along with the tetracycline, or don't take anything which contain divalent ions such as calcium, magnesium or aluminum. Should not take calcium supplements also if you are being treated with the tetracycline, because it will form a complex with this divalent ion, and this complex is not absorbable through your GIT. Assume this is the GIT, tetracyclines will be here, calcium will be here, they form a complex and this complex is not absorbable through the GIT. So in another hand, we can increase the absorption or bioavailability of indomethacin and barbiturates by forming a complex with the beta cyclodextrin. So by forming a complex with beta cyclodextrin, it will increase the solubility, hence it will increase the absorption and also it will increase the bioavailability. And the next one is reducing the toxicity. The cyclodextrin, say beta cyclodextrin, are effective in reducing the ulcerogenic effect of indomethacin and local tissue toxicity of chlorpromazine. So whatever the cyclodextrins we have, this cyclodextrin, if you form a complex of indomethacin with the cyclodextrin, the ulcerogenic activity of indomethacin, if you take indomethacin, there is a probable chance that you will get ulcers. This chance is reduced by forming a complex with the beta cyclodextrins, and your chlorpromazine has local tissue toxicity. This local tissue toxicity activity of chlorpromazine can be reduced by forming a complex with the cyclodextrin. That's what this point is. Next is antidote for metal poisoning. If you have metal poisoning, we can form a complex with the metal, and this complex is very soluble and it is removed from the body very easily. We try to see the example here. Toxic metals such as arsenic, mercury, antimony, etc. bind to the SH group of various enzymes and interfere with the normal functions. That's how they cause metal toxicity. These toxic metals bind to the SH group of the enzyme and they cause the problems in normal functions. Now, compounds like dimercaprol, we call it as BAL, British anti-levisite. Okay, this dimercaprol forms a complex with antimony or mercury or arsenic, and this is very water soluble. See, compared to plain metal, arsenic is there, its solubility is less. When you form the complex with BAL, the complex arsenic BAL complex is having more solubility compared to the arsenic itself. So the property of the complex is the solubility is more, hence you can remove that drug easily from the body. Okay. Other examples are beryllium poisoning can be reduced by salicylic acid. Salicylic acid is a complexing agent here, and lead poisoning can be removed by EDTA, by adding EDTA into the body. So if anybody is suffering from this type of metal poisoning, you can use these complexing agents to reduce that poison. Next we have drug action through metal poison. See here, 8-hydroxychloroquinone can complex with iron that is normally present in the body. Now this complex can penetrate through the cell membrane of malarial parasite, okay, leading to the accumulation of excess metal in the body of the parasite, thus provide better malarial action. Hydrochloroquinone, okay, hydrochloroquinone is used for the it is anti-malarial drug. Now, if you've made a complex, if you give plain drug as such, it doesn't have so much effect compared to the drug complex with the metal ion, that is your iron. So, if you give 8-hydroxychloroquinone quinoline in the body, this will form a complex with the iron present in the body, and it enter into the parasite cell very easily. So, for the chloroquinoline to show the antimicrobial activity on the parasite, malarial parasite, it has to enter into the body of the malarial parasite. So, by forming a complex with the iron, it is very easily penetrated through the complex. This complex can be very easily penetrated through the cell wall of your malarial parasite, and which will increase its antimicrobial or anti-malarial activity. Then we have antibacterial activity. So, anti-tubercular drug such as PAS, aminosalicylic acid, para-aminosalicylic acid, is known to form cupric complex and also chelates. So, this anti-tubercular drug, para-aminosalicylic acid, is known to form a complex with the copper ion, and also it also forms the chelates. Now, the cupric chelates has shown greater in vivo anti-tubercular activity in the mice compared to normal para-aminosalicylic acid. So, para-aminosalicylic acid is used for treating tuberculosis. What they found is, when you add a complex of para-aminosalicylic acid with the copper, which forms a chelate with the copper, it has more antibacterial activity compared to the plain para-aminosalicylic acid. Next, why it is like that? What is the reason why it is having more antibacterial or anti-tubercular activities? That formed complex is 30 times more fat soluble than normal complex. So, the cupric complex formed by your para-aminosalicylic acid is more soluble than the more soluble in fat, not in water. Here the solubility of drug is been decreased, okay, or you can say fat solubility is increased. So, the fat solubility is increased, and the bacterial cell wall is more fatty, hence it helps the drug to penetrate through the bacterial cell wall and shows more anti-tubercular activity than the ion itself. Okay. Now, apart from this, we have several applications related to drug protein binding, which is also important in pharmacy. We study this drug protein binding in the biopharmaceutics and pharmacokinetics, BPPK. Okay, so we will move on to the classification. Now we will see about the classification. After the introduction of the complexation, now we try to see about the classification of complex. Yeah, after the introduction of complexation, now we will see about the classification of complexation. So, it has been classified into 3, 1, 2 and 3. The first one is metal complex. Metal complex again classified into inorganic type, chelates, olefins, aromatics. Then organic molecular complex are classified into drug caffeine complex, polymer complex, picric acid and quinhydrone complex. Inclusion complex are channel type, layer type, Clatherates and monomolecular complex. We try to see what is the description about these complexes in detail. Yes, the first one is metal complex. Metal complex constitute of what it contains, as the name suggests, we have something called metal ion and has a central atom. So, we will have metal ion as a central atom, or you can call it as a substrate. Remember GPAT question, in a metal complex, what is the substrate? The substrate is metal ion. which interacts with the electron pair donor, or we can say ligand. Electron pair donor or ligand, it will form interaction with this, or we call it as a basis. It will form an interaction. The substrate will form interaction with the base, or we can call it as central atom, that is metal ion, will form complex with the electron pair donor, that is ligand, forming coordinate bonds between the two species, that is your metal ion and ligand. So, we will see what are those. So, metal ion complex are again classified into first one. The first classification is inorganic complex. Now, there is a scientist called Warner. He has coined some postulates or rules. Okay, postulates or rules which guide what is your metal complex looks like. Okay, so we will try to see his postulates. Okay, what is his postulates? One is, there are two types of valencies in a metal, or you can say inorganic complex. In an inorganic metal complex, there are two types of valencies. One is primary valency, which we call it as ionic valency. Second is coordinate valency, or we can say secondary valency. This is the first postulate. Then so we can clearly see here we have central atom, then we have ionization sphere. So, this ionization sphere we call it as primary valency. Whatever the coordination sphere is there, we call it as secondary valency. Yeah, check in this. Some type of ion, same type of ion, or you can say radical or molecule, can satisfy your both primary and secondary valency. See in this case of chlorine, chlorine is there in ionization sphere as well as coordination sphere. Both type of valency is being satisfied by chlorine in this case. Next, for each, third postulate says, for each central atom, central ion, there is a fixed number, what we call it as coordination number. There is a fixed number of non-ionic valencies, this one. Whatever the coordination number you are seeing here, okay, the cobalt has coordination number is 6. In among it, 1 is chlorine and 5 is NH3. That is the coordination number of central atom. So, it has fixed number, or you can say coordinate number, or fixed number of non-ionic valencies. Those valencies are non-ionic, we know that. Coordinate valency. Okay. Next is the coordinate atoms or groups occupy first sphere or coordination sphere, then other atoms said to be occupy second sphere, that is ionization sphere. Remember, here there is a confusion about the valency and sphere. He says valency primary is ionic, then he say sphere secondary is ionic. So, remember here, to avoid your confusion, valency primary ionic, in case of sphere secondary ionic. Okay, so in case of sphere we are going to call ionic as secondary, but in case of valency we call it as ionic valency as primary valency. Remember this, it will cause so much confusion. Okay, then a neutral, fourth postulate says, neutral molecule as well as ions may satisfy non-ionic valence. We can see here NH3 is a neutral and also we have chlorine. So, both can satisfy your, chlorine is an ionic molecule, ionic atom, both can satisfy your coordination number, non-ionic valence. Then coordination number and non-ionic valences are directed towards definite position, what we call it as stereoisomerization. So, they been directed in a definite position. Okay, we call it as stereoisomerism. It will be like this. See, cobalt will be here. Okay, we have NH3, this one and this one. So, this how one chlorine, NH3, then NH3. So, Non-ionic valencies are directed towards definite positions. Definite position is this one. The position of each valency will be definite. We call it as stereoisomerism. So these are the 5 postulates which has been coined by the Warner to explain uh, metal complexes inorganic. Then we will see the explanation for this. What it says is, in a solution, this compound ionized to form this molecule and this molecule. So we have ionization primary valency, that is 2, that is your chlorine. So we call it as primary valency is ionic valency, because that valency will get ionized when we keep that molecule in water, hence we call it as ionization sphere, or you can say ionic valency. Next, chlorine ion is coordinated sphere cannot be precipitated by silver. It means if the chlorine which is present here, this chlorine is present in the coordination sphere. This is can't be ionized. Obviously, if it is not ionized, it can't be precipitated by silver. But the chlorine which is present in ionic sphere can be precipitated by silver because it is ionizing. Next, groups such as chlorine and ammonia in coordinated sphere. So we have chlorine and ammonia in coordinated sphere, both chlorine and ammonia are called ligands. Okay, these always donate electrons to the central atom. We know that they are called ligands, they are always donate electrons to the central atom. Next is type of bonding between metal and ligand may be electrostatic or covalent. It can be anything, electrostatic or covalent. The bonding between metal ion, that is your cobalt here, this cobalt and these two ligands can be electrostatic or covalent bond. Next is the coordination number of central atom is the maximum number of atom or group that can combine with the central atom in the complex. So if I say coordination number is 8, the metal ion can complex with, or it can form ligands, or it can complex with the maximum number, that is 8 number of ligands. That what it means. Okay, then coordination number is usually an even number for cobalt, and coordination number is 6. For cobalt it is 6. So it will be usually an even number. Usually your coordination number is even. Remember this. Usually the coordination number is even. For cobalt it is 6. See, in this case also it is even. Now we will try to see what is the concept of hybridization. So how the complex is going to form, how it is different from the classical theory of valencies. Okay, let's say cobalt, we will take cobalt complex previously. So in the cobalt, ligands donate the lone pair of electron in forming the complex. So example for ligands are H2O, NH3, NC and Cl. In case of our complex, we have Cl and NH3 as a ligand. This electron pair is accepted by metal ion. So what are the metal ion which is present in the central sphere, coordination sphere? It will accept the electrons donated by the ligands. So in metal ions, all the orbitals such as S, P and D to be considered for the accounting of the complex. So for the formation of complex, all S, P and D orbitals are considered. We will see what is that. Here next is, check this one, the coordination number of cobalt is 6, the coordination number is 6. Okay, that what we saw there. So how that 6 is found, we will try to see it. The trivalent cobalt ion, so the cobalt ion is trivalent, has given electronic configuration in ground state. See, this is the ground state, this is the ground state electronic configuration of cobalt ion. Here the coordination number is 1, 2, 3, 4 only, but when it goes to excited state or during the formation of complex, the number will be increased to 6, coordination number will be increased to 6. Above it is 4, there are 4 orbitals which are this, 4 orbitals are ready to form a complex, but when it is going to form a complex, the number will increase to 6. So it includes all these articles to form a complex. How this happens, we will try to see here. So cobalt seems to make use of their 3d, 4s and 4p orbital. All this, just remove this one. Yeah, 3d, 4s and 4p orbitals. So it make use of all these three for forming hybridization. Okay, but this type is different from classical concept of hybridization. That's what I am saying. So this all 4 orbitals or all 3 orbitals 3d, 4s and 4p involving in hybridization is not explained by classical theory of valence. So in the classical theory, the electron pair is promoted to unfilled orbitals. So in the classical theory, the electron pair, if at all if want to promote, classical theory says, yeah, check this one, check here. The classical theory says this filled electron will be transferred to this one and it will be like this, and it will become only one electron like this. This is what explained by the classical theory. But in the complex, what happens? All this electron will go here and this electron will go here, and they will leave these 6 orbitals to form hybridization. We will try to see how is that happens. Okay. This half filled orbital further involved in the chemical bonding. Okay. Now in complex, so this half filled, whatever I said in the normal classical theory, this particular ion will be jumped here, it will be like this, and here nothing will be there. Whatever the half filled are there, all this will form complex. But in case of complex, that what is explained by classical theory. But in case of complex, the electron in half filled orbital shift to other orbital in order to fill them as a electron pair. That what happens. What happens in the complex is this electron will be shifted here, this is shifted here, this is shifted here, and they form filled orbitals. Okay, then this creates completely vacant orbital in the metal electronic configuration. Here 1, 2, 3, 4, 5, 6. 6 completely vacant. So they can readily accept 6 lone pair of electrons. Hence that we call it as a coordination number. We call it as a coordination number, and the coordination number for the cobalt is 6. The electronic configuration of metal ion leading to filled 3D level is, see here, these are the electronic configuration of the metal ion. This is how it looks. Now ligands donate lone pair of electrons. So one NH3 will donate here, another NH3 will donate here, Cl will donate here, then NH3 here, NH3 here and NH3 here. So in case of our cobalt, all these things will donate their electron pair because they have excess of electron. Hence we call them as a ligand, and they will donate the electron pair and they form a complex. Thus sp D2 sp3 or octahedral structure is predicted in complex using this technique. Warner has proved that the cobalt complex are octahedral. Thus the structure for octahedral is given here, this one. So there will be hybridization called D2. 2D molecules are involved. I will tell you how this hybridization looks. We call it as 2D molecules involved. So D2, 1S is involved, so S, and 3P are involved, so P3. So D2 sp3 hybridization is going to form in case of cobalt to form a complex with the ligand. That is what the explanation for the inorganic metal complex. Then we have chelates. What are chelates? Chelates are group of metal ion complexes in which substance, you can call it as ligand, provides 2 or more donor electron group to combine with the metal ion. So it will provide, one substance is going to provide 2 or more group, that we call it as chelate. Assume this is one substance. Initially what happens, we saw cobalt is there, 1, 2, 3, 4, 5, 6. 6 different substances are giving the lone pair of electron to the cobalt. All 6 different structures. But in chelates, there will be one molecule, there will be atoms in the molecule, then they will, 2 atoms, more than one atom will donate electron to the central atom. That is called chelate. Remember, in a molecule, if 2 or more atoms are donating the electron, we call it as chelates. Okay. In case of inorganic complex, one atom or one molecule will donate only one lone pair of electron. In this case, a molecule will donate more than one lone pair of electrons. that is called chelates. Two or more donor groups will be present in the same molecule. So, in inorganic complex the ligand provide only one side, that what I said, this is what the inorganic complex, but here in chelates the ligand will provide more than one sides. So, depending on the sides we will have bidentate, tridentate or polydentate. Bidentate is two sides, tridentate is three sides, polydentate is more than three sides. So, bidentate or you can say polydentate. Okay, best example for chelates is your EDTA, ethylene diamine tetraestic acid. Okay, so in this case you can see here I said you one molecule can donate more than one lone pair, that is here. In the EDTA we have this group and this group donating the electron. Okay, so two groups, two amino groups, okay, ethylene diamine. So, diamino, these two groups are donating electron to the metal ion. If they are forming a complex with the metal ion, these two groups are donating electron to the metal ion. Because one molecule itself is giving more than one site of forming a complex like donating a ion, so ligand, hence we call it as chelates. So, there is a usefulness of this EDTA chelates also is there. Okay, what is that? We can see here we can increase the stability or you can increase the solubility. So, we will see what are the uses. So, oxidative degradation, see if you have ascorbic acid, vitamin C, it will degrade very quickly by oxidation. If you put EDTA, if you complex EDTA with vitamin C, this vitamin C EDTA complex will have more stability compared to your normal complex. 1. 2. You can remove the ions present in the water without, or you can make the water soft without removing the ion present in the water. You will see we call hard water. Why we call it as hard water? Because many ions will be there in the water like metal ions. So, this property of metal ion can be suppressed without removing out. You can suppress it without removing out. That we call it as sequestering, or you can say removing. If you add EDTA to water, this EDTA will form a complex with the metal ion, and the property of metal ion is being suppressed because it is forming complex with the metal ion. Hence, the water will become soft, from hard to soft. But here the ion is not removed from the water, still it is present in the water, but now previously it is present in the ionic form, now it is present in the complex form. Its property is been suppressed, that what it is, sequestering. Then we can use EDTA complex for purification of water, that what I said now. Then we can use in the analysis of drug. How? The assay of procainamide, there is a injectable solution procainamide which forms 1:1 chelate form with cupric ion. So, 1 ratio of procainamide and 1 ratio of cupric ion, it forms complex at 4 to 4.5 pH. The chelate is colored complex and can be estimated colorimetrically. What you want to say is, if you want to get 1:1 ratio of procainamide and cupric acid, you need to form a complex between them. How you will come to know after forming the complex? The ratio is 1:1 by knowing the color of your solution. So, procainamide when reacts with the cupric ion, when it starts reacting with the cupric ion, the intensity of color will be less. As the complex is going to form with the ratio of 1:1, then the intensity of color will be more. You can estimate this by colorimetrically, that what he is saying. Next one is, you can use EDTA as anticoagulant. We already know citrates, oxalates and EDTA can be used as in vitro anticoagulants. Okay, what they will do is, we have dicalcium ion, that is divalent ion, that is calcium in our blood. This, if you can complex this calcium, sequestering, the property of calcium is being suppressed without removing it out, sequester. So, if you add EDTA to that blood, this EDTA will form complex with the calcium, it will sequester it, and it will, because calcium is very important in the pathway of clotting, Now the calcium property has been suppressed, so there will be no clotting, thus it will act as anticoagulant. And the last one is olefin and aromatic type. This is not much important in what we say that pharmacy, because these complexes are used as catalyst in the manufacture of bulk drugs, intermediates and analysis of drugs. Remember this. So what are the complexes which has been used for the catalyst, okay, in the manufacture of bulk drugs is olefinic and aromatic type. Remember this one. Next is your organic molecular complex. Now, organic molecular complex, the name says organic molecule. So, whatever the complex is going to form between the molecules, in that molecule your carbon atom will be there. That we call it as organic molecular complex. So, in organic molecular coordination complexes, components are organic molecule and these are held together by weak force or hydrogen bonding. Remember, in organic molecular complex, previously via metal ion, the ligands will be donating the electron to the metal ion and they will be held very strongly, but here we are going to see the weak bonds, that is your hydrogen bond, like hydrogen bond in case of organic molecular complex. Now, the same components can also form molecular compounds when experimental conditions are altered. Okay. Now, what is trying to say in this is, if you increase the temperature, if you conduct this experiment, take two organic molecules, keep the temperature low and start interacting with them, then what happens, they will form a complex. There will be weak bonds are formed between the two organic molecules. If you change the experimental condition, let's say if you increase the temperature, if the temperature of experiment is high when you are synthesizing, then what happens, they will directly form molecule instead of forming complex. So, two molecules will form a stronger bonds and form other molecule, third molecule, instead of forming a complex. That what this point is saying. Hence, there is a difference given between the complex and molecular compound. So, reaction occurs in cold condition, that what I said. For the complex to form, organic molecular complex, we do not need higher temperature, but to form a molecule, altogether new molecule, because new bonds are formed, you need higher temperature. Then weaker force of interactions are involved, here strong electrostatic interactions are involved. We know that in complex the interaction is weak, because it is a molecule, the interaction will be strong. These complexes cannot be separated from solution, hence difficult to identify them by physical and chemical means. Okay, they cannot be separated from the solution. Okay, but here, because it is altogether a new molecule, you can clearly separate it from the solution. Now, as observed, inorganic metal complex electron donor acceptor type of interaction exists in organic molecular complex. As we observed in the inorganic metal complex, we saw ligand is giving electron to the metal ion. Like that, here also donor acceptor thing will occur between the two molecules to form a organic molecular complex. So, the individual species are bound together by van der Waals force of attraction, that is what we saw. It contains weak force of attraction, or you can say dipole-dipole or induced dipole interaction or hydrogen bonding. So, these are the types of bonds which are formed between two organic molecules to form a complex. Thus, the forces are weaker forces. Okay, then, and the force is less than, energy is less than 5 kilo calorie per mole. The bond distance of the component is more than 3 angstroms. So, to form a stronger bond, the distance will be less. To form a weaker bonds, obviously the bond distance will be more. Hence, the covalent bond is not involved, because it is more than 3 angstroms. If less than that, the covalent bond will be involved. Then organic molecular complex, again we see the classification, classified as electron donor acceptor type and charge transfer complex. Okay, electron donor type, acceptor type and charge transfer type. We will see one by one. Electron donor type. Okay. So, in this type the bond is formed between two species but lacks charge transfer. Charge transfer will be not there, only electron donor and acceptor will be there. So, here dipole and London dispersion forces are responsible for stability. Take this example, N-dimethyl aniline and trinitroanisole. Here donor is your, we have lone pair of electron and the nitrogen. This nitrogen will donate the electron and this oxygen will drag this electron towards it. So, here donor acceptor type of interactions is going to take place, and this type of interaction leads to the formation of dipole or London dispersion. They will form stability between these two molecules. Okay. So, here this kind of interaction is going to occur. Next we have charge transfer complex. In this type one molecule will cause the charge transfer on the other molecule. How it is? We will try to see that. Take these two examples, this is the donor and this is the acceptor. So, we have benzene and trinitrobenzene, trinitrobenzene and benzene. So, what happens? For example, the polar nitro groups induce dipole in readily polarizable benzene molecule. Okay, see here, these three nitro groups which are present on the trinitrobenzene, they are already polar. When they come near to this benzene will get polarized. So, where it will drag, the oxygen will drag electron counts towards it, here it will form negative, where the electron count is less, here it will form partial positive. So, initially benzene does not have any charge, the charge is been induced. Okay, charge has been induced, hence we call it as charge transfer complexes. This how it forms. Now, because it forms negative here and we have positive charge here, this negative and positive will form an interaction between them and the bond is formed, that is weaker bond, and this complex is been stabilized. Okay. Now, next. So, organic molecular complex are again classified. These are the two types of interactions may be possible in the organic molecular complex. So, donor acceptor and charge transfer. They are classified into four types. First one is drug polymer complex, polymer complexes, then picric acid and quinhydrone. So, we will see first one, drug caffeine complex. So, in the drug caffeine complex, we have caffeine here, we have benzocaine here. What happens here is, the mechanism is dipole forces are hydrogen bond between the polarized carbonyl group of caffeine and hydrogen atom of the acid, or interaction between non-polar parts. So, how it happens we will try to see here. Check here, when these two come near to each other, the electron lone pair which is present here in this case, check the caffeine here, the electron lone pair which is present here, it has two options, it can go this side and it can go this side. If it goes this side, there will be double bond formed here and this double bond is shifted to the oxygen and it will form partial negative because electron is shifted there. That what happens if it go towards up. At the below, if this electron is going below like this, the electron double bond, the double bond will be formed here and this double bond will shifted here to form partial negative charge. So, the nitrogen will form partial positive and in either case two oxygen will form partial negative in case of caffeine. Check benzocaine. In the benzocaine, the electron lone pair which is present here is shifted here and there will be double bond formation here. This double bond will shift here and there will be double bond formation here. Again this double bond is shift here, double bond formation here, and whatever the double bond is here, it will shifted here and then oxygen will get partial negative charge and the nitrogen will get partial positive charge. Now, we have negative charges here as well as positive charge at this side. So, negative charge of this one and this one will interact with the positive charge of this one and positive charge of this one will interact with the negative charge of this one. Due to this interaction, the Riblet complex will be stabilized. This how the interaction will form between the drug caffeine complexes. Now, drug caffeine complex, if you we saw about the benzocaine, if you complex the caffeine with gentisic acid, if the caffeine is going to form complex with the gentisic acid, this gentisic acid is bitter in taste. If you form a complex with caffeine, the bitter taste can be masked, okay, by the complexation with the caffeine. Next, these drug caffeine complexes may enhance or inhibit the solubility and dissolution rate of drugs. Sometimes it will enhance the dissolution rate, sometimes it will inhibit the dissolution rate. As a result, they can improve or extend the absorption or bioavailability of drug. Okay, if you decrease the solubility, bioavailability is extended. If you increase the solubility, improve the absorption. Okay, that's what it happens. Next one is polymer complexes. So, in the polymer complex, there will be a complex formed between the polymer and a drug, which is not recommended in case of formulation. In the pre-formulation studies, while forming a formulation, the students who are doing project in pharmaceutics department, they will come to know this one. So, the primary thing which we test in the pre-formulation is the compatibility of your polymer and drug. Here what happens, polymer complex, your polymers such as PEG, polyethylene glycol and carboxymethyl cellulose contains nucleophilic oxygen within them. This will involve in the formation of complex with the drug. Example is polymer is carbovax and fluoronics, the drugs are tannic acid, salicylic acid and phenols. So, there is a formation of complex between these two, but we do not want them to form a complex because we are in the formulation. You will take formula 1, you will take drug, you take polymer 1, polymer 2, excipient 1, excipient 2, etc. Now, if this polymer 1 or 2 or excipient 1 or 2 is going to form a complex with the drug, then the intention of your formulation will be wasted. So, we do not want our polymer to form a complex with the drug. That what we are going to test the compatibility between the polymer and drug. To test that, we have FTR, Fourier transform IR spectroscopy, and also you can do it by DSC, differential scanning calorimetry, and we have many methods through which we can check the compatibility of polymers with the drug. So, for example, this type of complexation produce, it is given clearly, this type of complexation produce incompatibilities in the dosage form. Okay, incompatibility may be, it will delay the absorption or loss of preservative action or undesirable physical, chemical or pharmacological effect will be given. So, we do not want them to form a complex. Another one, polymer containers and drug products interaction may also result in the loss of active component in the liquid dosage form. Okay, so the example for this what I can give here is when you are injecting insulin through IV set. So, in the IV, so the polymer present in the IV set, that plastic polymer will try to interact with the insulin and it will hold insulin there itself. So, you will be thinking that insulin is going through the IV, it will be not going and it is not decreasing the blood sugar level for the patient whom they have to undergo any surgery. In case of surgery, if the blood sugar level is high, they will first decrease the blood sugar level, then they will take him to the surgery. To decrease the blood sugar level in a faster manner, in a less time, they will give insulin in IV. Because the insulin is forming complex with the IV set polymer, that plastic which is there, which is used to pass this IV fluid, in that pipe, it will going to form a complex with the polymer, that insulin is not entering in the body, but doctor is thinking that I have given this units of insulin, the blood sugar level decreased this much. So, you need to check this before that one. Okay. Similarly, we have preservatives, methyl paraben and propyl paraben. This paraben will absorb into the drug container. You have added this compound has a preservative, because they are adsorbed into the container, there will be no action of preservative action on the formulation, hence the formulation will be destroyed. So, we do not want that polymer complex to happen. Next is picric acid complex. This is very interesting. If you take picric acid, this is the picric acid. Picric acid will form a complex with many of the molecule. So, one of the molecule which it is going to form is butazene. So, the 1% butazene picrate of 1% is used for antiseptic activity. Okay, if you use plain butazene, the antiseptic activity will be not that much. If you use plain picric acid, then also it will be not that much. If you form a complex this between two, there will be a formation of a complex. How the complex is formed, we will try to see here. There will be lone pair here, this lone pair will be shifted here, there will be formation of double bond. Whatever the double bond is there here, it will shifted here. Okay, then whatever the double bond is there here, it will be shifted here, it will form double bond here, and this double bond will shift here and form negative, this will form positive, and this will attract the molecule, or you can say this nitro groups which are present here, 2 nitro groups or 3 nitro groups are present here, will induce the ionization in the butazene. This will be this how the ionization will form, and they will form an interaction and form a bond. That is the one. So, butazene picrate is used for antimicrobial activity in 1%. It is also having one more good property, that is you can estimate the, let us say I have given you one drug, you want to know what is the carcinogenic activity of this drug. We do not know if the drug is causing cancer, how much it is causing cancer, we want to know its carcinogenicity. In that case, make the drug to form complex with the picric acid and measure the stability constant of the complex, measure the stability constant, see stability constant of the complex. If the stability constant is high, it indicates the drug is having high carcinogenic activity. If the stability constant of the resultant complex with the picric acid is less, it indicates the drug is having less carcinogenic activity. So, this is also one important usefulness of picric acid complex. Yes, the next complex is quinhydrone complex. It is obtained by mixing the hydroquinone and benzoquinone by taking their respective alcoholic solution. Let us say this is the hydroquinone, this is the benzoquinone, is their alcoholic solution. Mix them in equimolar concentration, that is 1:1 ratio, any ratio 2:2, 3:3, 4:4, equimolar concentration. The resultant will be a crystal, green crystal, which is a complex, we call it as quinhydrone complex. Now, to separate this complex, again this is the alcoholic mixture, this is the alcoholic mixture, add this mixture to water and take the concentration till saturation. If you take a saturated solution, when you add this compound, they will be separated into individual hydroquinone and benzoquinone complex. Now, how the reaction is formed, how the complexation is formed here? Here there is a overlapping of pi bonds. There will be a overlapping of pi bonds. Then the hydrogen bond which is formed here, this one and this one, this hydrogen bond will stabilize the complex. So, there will be overlapping of pi bonds, and this overlap and formed complex is stabilized by hydrogen bonds. Move on to next thing, that is inclusion complex. The names suggest inclusion means something is included inside something. So, we also call it as occlusion complex, in which one of the component is entrapped in the open lattice or cage like structure of other. So, one will be there like this, inside it, if assume we have a complex something, not complex, a molecule like this molecule, half molecule will be inside, half molecule will be outside. It may be half, it may be part, it may be anything. That is the reason we call it as occlusion complex. one of the components, it may be half component, full component of molecule will be entrapped in the other molecule, that we call it as inclusion complex. So in the inclusion complex, the first one is channel type. The channel type, the best example is here, the molecule which is taking the other molecule, we call it as a guest molecule. The molecule which is entering into a one molecule, we call it as a host molecule. Here the guest molecule is your urea. So urea is your sorry here the guest molecule is methyl L alpha lipolate. Methyl alpha lipolate is your guest molecule and urea is your host molecule. So what is happening here? So channel type, see here what is happening, the methyl alpha lipolate is like this. It's a long channel is there here. Okay, in this channel our urea is entrapped inside. Yeah, next one is channel type. In this inclusion complex, first one is channel type. The molecule which is including one molecule, we call it as a host molecule. The molecule which is going to include, we call it as a guest molecule. So there are two things. One molecule will be like this. The molecule which is inside, we call it as, this will be your guest molecule and this will be your host molecule. So the example one here is urea. Urea is acting as a host and your methyl alpha lipolate is acting as a guest. So this methyl alpha lipolate is entering inside the channel type formation of urea. See here, urea has this type of structure, channel, long channel. Okay, in this long channel your methyl alpha lipolate is included. Another example is iodine and starch. So starch will be like this, full channel. The iodine will be entrapped here. It will be like this. I will draw here like this. Spiral channel will be there. If you see this from this side, it will be like this. So there will be full channel inside. Okay. So iodine will be entrapped here like this. This iodine and starch also form channel type complexes. This is the one example. Now, what is the applications of this channel type is separation of optical isomers. To separate optical isomers, let us say D and L terpineol is there. It can be resolved. We have a mixture of racemic mixture of D terpineol and L terpineol. Okay, in a beaker we have two mixtures, both D and L terpineol. I want to resolve them. I want to separate D and L. In this case, use digitoxin. Sorry, digitonin. If you add digitonin to this, digitonin will form complex with only one type of, either it will form complex with D type of terpineol or L type of terpineol. So it can be resolved. So the complex formed can be separated and the individual terpineol can be left out in the beaker. So if it is forming complex with the D type, all D type D terpineol with digitonin complex will be separated and L will be remaining in this beaker. Then in the analysis of dermatological creams, long chain compounds may interfere in the assay method. Such ingredients are removed by use of channel type of complexation with urea. So we have dermatological creams, the creams which are used for your dermatitis, applying on the skin. In that you may be added your one of the excipient. We have drug, we have excipient 1, excipient 2, excipient 3 in the dermatology cream. Okay, in that cream, let's say the excipient 2 is a long chain excipient. This long chain excipient can be removed by the use of urea. urea is a channel type, we can remove it by the use of urea. Okay, because they will cause problem in the estimation of content of drug in the cream. If you want to estimate how much drug is present in the cream, in that estimation, because your excipient 2 is a long chain, it will interfere in that assay. It is better to remove them, then go ahead for the assay. Then we have layer type. So layer type easily indicates we have something layers like this. In this layer, the host molecule will be layer and the guest molecule will be entrapped in the layers. Example for this is monomolecular, that is your clay. Okay, example is bentonite. So bentonite or monomolecular is in layer type and it can entrap the hydrocarbons, alcohols and glyols. So your guest molecules are hydrocarbons, alcohols and glyols, and the host molecule here is bentonite. They form monomolecular monoatomic layer. So monoatomic layers of guest and host. So one atomic layer of your guest, then we have another atomic layer of host and guest, like this. That what it says. Okay, what he is saying is, where can we use this is for the catalysis, because they contain large surface area. You can use this bentonite for catalysis because they contain large surface area. Next is Clatherates. Warfarin sodium, which we use here as anticoagulant, it is a catharate of water and isopropyl alcohol. We will see what is that. Okay, it is available in white crystalline powder. Okay, during crystallization, certain substance form cage-like lattice. So while forming a crystal, some substance form cage-like lattice. In that cage, see here, this is the cage formed by the substance. Okay, in this cage we have molecule which is entrapped here inside. Here inside we have entrapped molecule. This is the substance which is going to form cage. How it is going to form cage, we will try to see now. Okay, here the example is for us Quinhydrone molecules. Okay, small molecules are entrapped in the Quinhydrone molecules. See here, let us say Quinhydrone structure is OH and OH. So one structure here, another structure here, another here, another here, another one. So here also OH, another quinhydrone, OH, 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 so here this bonds are, this looks like benzene, don't think it has a benzene. See here, that what the confusion is. This looks like benzene, don't think it has cage like benzene, cage like structure is been found by Quinhydrone molecule, and these bonds are hydrogen bonds. What are the bonds you are seeing here? That is the reason they are denoted in dots. These bonds are hydrogen bonds. In this cage, what are the molecule is written here like this? It can be a square molecule, it can be this molecule, anything. It is entrapped. I write a square molecule, it is entrapped inside like this. By seeing this structure like this, the people will assume it is a benzene structure. Don't get confused here. Okay, that what is your Quinhydrone. Applications, you can use this as a molecular sieving because they form a cage like structure. You can sieve the molecules. Some molecules are entrapped here, some molecules will go away from this, they will not entrap. So if you want to remove some molecules, you want to sieve the molecules, you can sieve the molecular mixture with the help of this type of cage formation. That is the use of your Quinhydrone complex, or you can say Clatherates. Okay, you can remove the, see in the Clatherates you can remove the guest molecule just by simple physical process. So after molecular sieving, some molecules which are entrapped in the cage like structure, those molecules can be removed by simple physical process. Okay, just change the temperature or something, it can be removed. Next is monomolecular inclusion complex. The name says monomolecular inclusion complex. One molecule will be included in the other molecule. So that what is it is, okay. One inside one molecule, other molecule is included. Monomolecular inclusion complex. The best example here is beta cyclodextrin. See the beta cyclodextrin. This is the structure of beta cyclodextrin. So host molecule, that is your beta cyclodextrin. Inside, at the entrance, the beta cyclodextrin has hydrophilic entrance. Okay. Okay. Interior will be hydrophobic. Outside will be hydrophilic. This one, and inside will be hydrophobic. So interior will be hydrophobic. Now what happens? If you put any molecule, one molecule which is hydrophobic, let's say I am taking this molecule OH and COOH. This molecule, if you introduce, this part is hydrophobic and these two tend to be hydrophilic. Now this molecule will sit inside like this. The benzene will be inside and the hydrophilic molecule will be outside. So this how it will sit inside. So one molecule is sitting inside one molecule, hence we call it as monomolecular complex. What is the use of this monomolecular complex? Because the outer, I said interior is hydrophobic and exterior is hydrophilic. Okay, you can, because it is hydrophilic, you can enhance the solubility. Exterior is hydrophilic. Okay, so enhance the solubility, enhance the dissolution. You can also enhance the stability, because one molecule is going and sitting inside the other molecule. Whatever the molecule which is destroyed by the environmental forces, oxidation or hydrolysis, can be reduced by complexing with the beta cyclodextrin, like the aspirin. Aspirin is aspirin, benzocaine, ephedrine, testosterone. If you make complex with the beta cyclodextrin, their stability, their oxidation or hydrolysis process will be decreased, because they went and sit inside one molecule. Their groups are not exposed for oxidation hydrolysis. Like that, their stability is increased. You can also use it for sustained release, because the molecule is going and sitting inside the beta cyclodextrin. We can also use it for sustained release. Remember, okay, ethylated beta cyclodextrin. If I modify the structure of beta cyclodextrin, if I ethylate it, if you add a ethyl group to the beta cyclodextrin, if it is not ethylated, see, if it is not ethylated, it will increase the solubility. If it is ethylated, it will decrease the solubility and it can be used as a sustained release. So it retards the release of drugs such as diltiazem and isosorbate dinitrate with when complex. This drug release slowly for prolonged period of time and provides sustained effect. Sustained means the release of the drug is being sustained and the effect will be seen for the longer. So these are the complexes we have. Inclusion complex. So this completes the classification. Next we move on to the analysis of complex.